Welcome to lecture 4.6, Automorphisms. In the previous lecture, we learned about isomorphisms, which was a structure-preserving map between two groups, and here the word auto means self, so an automorphism is a structure-preserving map from a group to itself. Formally, we say an automorphism is an isomorphism from a group to itself. Since the domain and the codomain of an automorphism are the same, we can compose automorphisms, and it turns out that the set of all automorphisms of a group G forms a group. And this is called the automorphism group of G, and we denote it like this, aut of G. And it's very simple to show that this forms a group. The identity map is clearly an automorphism. Every automorphism has an inverse, that's just the inverse map because it's a bijection. And clearly, if you compose two automorphisms, you get an automorphism. Several remarks. First of all, an automorphism is determined by where it sends the generators. For whatever set of generators you want to pick, just fix one. Once you send the generators somewhere, everything else is determined. Also, any automorphism must send generators to generators. In particular, if G is cyclic, recall that this means that it can be generated by a single element, although there might be a collection of elements which are potential generators. In that case, it determines a permutation of the set of all possible generators. Let's do some examples. First, I claim that there are only two automorphisms of the group of integers under addition. That's denoted Z. These automorphisms are the identity mapping and the mapping that sends every integer n to its negative. And to see why these are the only two automorphisms, well, I claim that this follows just from these two remarks up here. First of all, an automorphism is determined by where it sends the generators. Now Z is of course generated by 1. But it's also generated by -1, and these are the only two generators of the integers. So there are two choices for where 1 gets sent, because it has to send a generator to a generator. 1 can either get sent to itself, which is the identity mapping, or it can get sent to -1, which is the other mapping. Also, as I said in the second remark, if G is cyclic, like the integers are, then it determines a permutation of the set of generators. So this first automorphism, the identity, is just the identity permutation. It sends 1 to 1, and -1 to -1, and the other mapping swaps these two. So the automorphism group of the integers, since it has size 2, is isomorphic to the cyclic group C2, or you can call it Z2 if you prefer, or you can call it S2 because it's a permutation of two elements. These are of course all the same. Next, let's look at the automorphisms of a finite cyclic group, and we'll do Z5. So as before, an automorphism is determined by where it sends the generators, and Z5 is of course generated by 1, so an automorphism phi is determined by the choice of the image of 1, phi of 1. And there are 4 choices, because phi of 1 can be any of the 4 other generators, namely 1, 2, 3, or 4. Because all 4 of these are relatively prime to 5. So obviously each of these is a distinct automorphism, so there are 4 automorphisms of Z5, which means that the automorphism group has order 4, so it must be isomorphic to either the cyclic group, C4, or the client 4 group, V4. Let me ask you, open-ended question, which one? How would you determine this? So think about this. I would check each of these automorphisms and see if any of them generates the entire group. In other words, if any of them have order 4. If that's the case, then the group is C4. If all of these automorphisms have order 2, then it's V4. So we will answer this on the next slide. Finally, let's do an example that's not cyclic. So V4, of course, is the smallest non-cyclic group, and that's generated by H and V, so this is horizontal flip and vertical flip. So an automorphism phi of this group is determined by where it sends H and where it sends V. These are the generators. Now there are three choices for phi of H. We can send H to itself, send it to V, or we can send it to the other element of order 2, which is HV. Once we do that, then there are two choices for where we send V. Well, we can't send it to the same place as we send H, and we can't send it to the identity. Therefore, the size of the automorphism group of V4 has to be 6. And there are only two groups of order 6 up to isomorphism. Namely, there's the cyclic group C6, which is isomorphic to C2 cross C3, and there is the symmetric group S3, which is isomorphic to D3 as well. So which one of these is the automorphism group? Well, it's pretty easy to check. Just take the automorphisms of V4 and see if they form an abelian group or a non-abelian group. And that should answer your question. And we will do this later in the lecture. Let's turn our attention to the automorphisms of finite cyclic groups. First, we need a definition. The multiplicative group of integers modulo n, sometimes we denote that as Zn raised to a star, or sometimes we put a time symbol up here. Although we will usually use this notation, U of n. This stands for the units, which is a term that we will understand when we study rings later in the class. This is the group of all integers modulo n that are relatively prime to n. And the binary operation is multiplication modulo n. So recall that if we look at the integers Zn, they always form a group under addition, but they don't necessarily form a group under multiplication. Because we could have things like in Z4, we might have 2 times 2 equals 4, which is 0, and that's not allowed. However, if we only take the numbers that are relatively prime to n, we never have this issue, and we actually get a group, and so we denote that as un. Let's do some examples. We'll start with u5. So this is the group of these four numbers, 1, 2, 3, and 4. These are the ones that are relatively prime to 5. And here's the multiplication table. So it's a group of order 4, and we can see it's not the Klein 4 group because there are not 1s down this diagonal. So this has to be isomorphic to the cyclic group, C4. Next, U of 6, or just U6, is the group consisting of 1 and 5. Those are the only two numbers less than 6, relatively prime to 6. So there's only one group of order 2, so this is isomorphic to the cyclic group C2. Finally, U8 consists of the numbers 1, 3, 5, and 7. These are the ones that are relatively prime to 8. And looking at the multiplication table, you can see right away that this has to be the Klein 4 group because all of the elements have order 2 because there's 1s down the main diagonal. So this group is isomorphic to C2 cross C2. So it's not always clear, given a number, what group UN is going to be isomorphic to. Because here's two different groups that have order 4. One of them is cyclic, one of them is not. Here's a proposition that you will prove on the homework. And it says that the automorphism group of Zn, which is just aut of Zn, is isomorphic to Un. So for each element in Un, we can define an automorphism. Let's call it sigma A. So it's a mapping from Zn to Zn that sends 1 to A. So that's what we did in the previous slide. Recall we looked at the automorphisms of Z4. So mapping from Z4 to Z4 was determined by where it sent 1, and there were 4 possibilities. There was 1, 2, 3, and 4. And that's because these are the numbers that are in the group U5. These are the numbers that are relatively prime to 5, so they are the generators of Z4. So similarly, the automorphism group of Z8 is determined, so a mapping from Z8 to Z8 is determined by phi of 1, and it has to send it to a generator of Z8. So there are 4 choices, 1, 3, 5, and 7. 1, 3, 5, and 7. And composition of these maps essentially is just multiplication of the corresponding numbers. So the actual multiplication table of the automorphism group is what you would get if you had this table, but instead of the numbers, you would put sigma sub the number. So instead of this 5, you would put a sigma 5. Instead of this 3, it would be a sigma 3, and so forth. So that's why these things are isomorphic. UN is the group of these numbers under multiplication, and the automorphism group of Zn is technically the group of these mappings, sigma A, where A comes from UN. So you'll prove this on the homework, but hopefully it's clear from these examples why this is true. Next, I want to find the automorphisms of D3, which is generated by R and F. And I particularly want to do this group because we will see a very similar example to this when we study Galois theory later in the course. Clearly, every automorphism phi is completely determined by where it sends the generators. So namely, determined by phi of R and phi of F. Since automorphisms preserve order, it's a structure-preserving map, then if phi is an automorphism of D3, then it has to send the identity to the identity. It has to send R to either R or R squared, and there are 2 such choices. And it has to send F to either F, RF, or R squared F. These are the elements of order 3, and these are the elements of order 2. Now, I'm not saying that every choice is going to work. Rather, what I am saying is that there are at most 6 automorphisms of D3. There can't be any more than that. Next, let's try to define 2 maps. I'm going to first define alpha to be an automorphism that fixes R, and it's going to do something to F. And then I will define beta to be an automorphism that fixes F and does something to R. So alpha will send R to R, and it sends F to RF. So this reflection to this other reflection. And beta will send R to R squared, or you can think of this as R to the negative 1. So it sends a 120 degree rotation clockwise to a 120 degree rotation counterclockwise. And it fixes F. I claim that both of these define automorphisms, and I encourage you to check this. In other words, that this defines a map that's a bijection. So in other words, compute alpha of R squared, compute alpha of RF, alpha of R squared F, and so on, and that we in fact do get a bijective homomorphism. That's not hard. And I claim that these generate 6 different automorphisms. And therefore, these 2 automorphisms generate the entire automorphism group of D3. To determine what group this is isomorphic to, and there's only 2 choices, it's either the abelian group of order 6, which is cyclic, or it's isomorphic to D3, which is isomorphic to S3. To do this, you would find these 6 automorphisms, and you can make a group presentation, or you can make a multiplication table. And the first thing I would ask is this an abelian group? If you can answer that, then you can tell me right away which of these 2 choices it has to be. Let's do this. Now, I claim that an automorphism can be thought of as a rewiring of the Cayley diagram. And this is best seen by example. So let's start with the identity automorphism. So it fixes R and it fixes F. And here are 2 different layouts for the Cayley diagram of D3. The first one is the one that we're most familiar with generators R and F. But the other one we've seen a little bit. This is generated by two reflections, namely by F and by R squared F. We could have chosen RF if we had wanted to. Here is the automorphism alpha. So it sends R to R. So it fixes R, meaning it fixes this red arrow, and it sends F to RF. So it sends this blue arrow, which is F, to RF. So you can see how this diagram is rewiring of this diagram. Alternatively, if we were to look at this Cayley diagram to begin with, and I'm putting both of these because I think they both offer a unique perspective, then this automorphism alpha, it does not fix either F or R squared F. You can check that it sends, so we've said F to RF, so it sends this blue arrow to this blue arrow, and it sends R squared F to F. It's easy to check. So it sends this green arrow to that green arrow, and this is what we get. Here is alpha squared, so we do this rewiring twice. So again, R is fixed, the red arrows don't change, but the blue arrows, now F gets sent to R squared F. So the blue arrow goes from E to R squared F. And this is the rewiring that we get in the other diagram. This is not obvious right away, but it's something you could check by writing out where alpha squared sends these elements, namely F and R squared F to. Now here's the other automorphism I defined in the previous slide. It fixes F and it sends R to R squared, or to R inverse if you prefer. Now this is going to fix all of the blue arrows because those correspond with F, but it's going to rewire the red arrows. So instead of E going to R, E is going to go to R squared. So it just reverses them. And it's going to change the green arrows as well. It's not hard to check that beta sends R squared F to RF. So this is the rewiring of the diagrams for beta. Now let's look at alpha beta. And I want to emphasize that when I'm writing it like this, alpha beta, I'm writing it in left to right order. So it's not like function composition. So by this I really mean alpha of beta. And it's not hard to check that what this does is rewires the diagrams like shown. And finally, alpha squared beta is this rewiring. So here are the 6 automorphisms of D3 seen as rewirings of 2 different Cayley diagrams of this group. I think this is pretty enlightening. It helps to visualize what these things are. So when you do alpha, you are rewiring the blue arrows like this, and you're fixing the red ones. And when you do beta, you're just reversing the red arrows. So beta is an automorphism that has order 2, and alpha is an automorphism that has order 3. Now that we have explicitly written out the 6 elements of the automorphism group of D3, we can construct the multiplication table, which is shown here on the left. And as before, I am expressing things from left to right, and so doing alpha and then beta is alpha times beta, which is, as functions, beta of alpha. So do alpha first and then do beta. The Cayley diagram is shown here on the right, and again I have used orange for alpha and purple for beta, just like I do over in the multiplication table. And now it's easy to see that this automorphism group is isomorphic to D3. It's worth mentioning that it's purely a coincidence that the automorphism group of D3 is isomorphic to itself. That usually doesn't happen. For example, we've already seen that the automorphism group of Z5 is isomorphic to C4. The automorphism group of Z6 is isomorphic to C2. And the automorphism group of Z8 is isomorphic to C2 cross C2. We'll conclude this lecture by returning to an example that we saw in the beginning, that is the automorphisms of the group V4, which is generated by a horizontal flip and a vertical flip. So here's the Cayley diagram using H and V as generators, and I claim that the following permutations of elements are both automorphisms. So alpha is going to be the map that sends H to V, V to HV, and HV to H. Remember that all three of these elements have order 2. And beta is the map that swaps H and V. So here's the identity automorphism that just does nothing, and here's the identity rewiring. Here is the map alpha that sends H to V, so that means the blue arrow gets sent to where the red arrow is, so the blue arrow gets sent down here and down here. And then V gets sent to HV, so the red arrow gets sent diagonally over here, and then HV gets sent to H. If we do this twice, then the blue arrow H gets sent to HV, so that's diagonally down like this. And then V, the red arrow, gets sent to H, so the red arrow gets sent here. So we have this rewiring. Now if we do beta, we're swapping H and V, so that just swaps the colors, red and blue. Next, let's do alpha and then beta. And again, I'm reading here left to right, as opposed to right to left as in function composition. And notice that's not what you get when you do alpha and then you swap the colors. So to see what you get, let's look at these permutations. So H goes to V via alpha, and then via beta, V goes back to H, so H is fixed. V goes to HV for alpha, and then HV is fixed by beta, so V goes to HV. And finally, HV goes to H by alpha, and then H goes to V by beta, so HV goes to V. And here's the rewiring of that. Finally, this is alpha squared, then beta. It's the sixth and final rewiring. These are where the generators get sent to, and this is the rewiring of the Cayley diagram. I'll let you check those details using these permutations on your own, just like how I did for alpha beta. And finally, on the last slide, here is the multiplication table and the Cayley diagram of the automorphism group of V4. As we observed, it is generated by alpha and by beta. So it is isomorphic to either S3 or D3 if you prefer. In other words, every permutation of V, H, and HV generates an automorphism. Obviously, the identity element has to be fixed. So here is the multiplication table of this. Notice it is just like the multiplication table of the automorphism group of D3. The only difference is alpha and beta represent different automorphisms because we're looking at a different group. And also notice that the Cayley diagram is just like, has the same structure as the one for D3 as well. The only difference is that the actual rewirings, the actual automorphisms in here, are different. Finally, as I've been saying, alpha and beta can be thought of as these permutations. And so the automorphism group of G is isomorphic to a subgroup of the symmetric group Sn. In other words, it is isomorphic to a set of permutations of the group elements. Notice it's never going to be equal to the entire symmetric group because every automorphism fixes the identity element. So if I wanted to, I could say even a little bit more. I could say, well, I could replace this G with G take away the identity element, because the identity element is always fixed by an automorphism. And I could replace Sn with Sn minus 1. And usually, the set of automorphisms is much, much less than the set of all permutations of the non-identity elements. However, in this case, because the group is small enough, it's actually the entire thing. The automorphism group of V4 is indeed isomorphic to S3.